behind the podium, all right? No one can see. Yes. I'm about to black out. I'm not gonna see y'all. I already took a lot. Yeah. If someone sneaks up behind me, just like, is this thing on? All right. Let's get started. Well, thank you everyone for calming today. I'm just kidding. I'm going to talk about comm hijacks. A little bit of background about me. My name is David Toulis. I'm an offensive security practitioner and researcher. I currently work for NCC Group. I lead red teams. I do Windows and AD pen testing, social engineering, physical security tests. This is a picture of me getting into a building that I have absolutely no business being in. You know what they say about being able to get anywhere you want if you're wearing a reflective vest? That is completely true. So what am I going to talk about today? I'm going to start by going over the basics of comm, understanding why it exists and how it works. I'll talk about the vulnerability in the comm activation process, how to identify hijack events on a system, followed by demonstrations of how an attacker can hijack objects to have their code loaded by other processes. I'll talk about some practical usages in offensive operations and then some takeaways for red and blue teams. So why the interest in comm? So comm is available in all versions of Windows dating back to Windows 3.1. Abuse of the comm object loading process will cause other processes to load arbitrary libraries of the attacker's choice. Depending on the details of how this is done, this can be used for persistence, for defense evasion, for lateral movement. Comm hijacking has been observed in the wild, mostly just for persistence. It's registered on the MITRE ATT&CK framework as Technique 1122. And for how useful and versatile this technique is, I don't think it's talked about nearly enough as it should be, so I want to show you all how cool comm hijacking is. COM is a very interesting interface for attackers, and unless you have previous experience in COM development, it's likely just a magical black box. So COM stands for the Component Object Model. It's been around since 1992, so this interface is actually older than me. You can imagine how archaic the interface is after almost 30 years of age. But COM is the fundamental framework behind many other Microsoft technologies, including ActiveX, OLE, COM+, DCOM, and more. You know how in Unix everything is a file? Well, in Windows everything is an object, and COM gives developers a language-neutral way of implementing objects that can be called by other processes. This allows programs which are written by other vendors in other languages to reuse objects and methods from COM-enabled libraries without any knowledge of the internals. This flexibility allows for implementation internals to change without requiring developers to recompile applications to account for updates in a library's binary structure. COM gives us the ability to interact with other programs. If you've ever embedded an Excel sheet in a Word doc, this is handled by Microsoft Word activating various Excel COM objects and then calling their methods to show you these Excel features all from within Word, and there's no Excel.exe required for this. Here's another example. If you've ever created a malicious VBA macro, then you've probably created a wscript.shell COM object and used that object to run arbitrary shell commands from VBA using that object's run method. Or maybe if you're familiar with James Forshaw's .NET to JScript project, that magical black box of .NET in, VBA out, that's all done through the creation of certain COM objects which expose the .NET runtime from VBA. Why does COM need to exist? Well, Windows is full of libraries. They're used to pass around objects and functions between processes, and this is all done through library files. So put on your developer hat, pretend you're a developer. You want to distribute a library so that other programs can interact with your program. So you can provide a statically linked library. In Windows, these are .lib files. This means that anybody who wants to use your library must compile their program against your library. Any updates you make to your library, you then must distribute those updates to developers who must recompile against the new version. Plus, you can have multiple versions of the same library existing on disk or in memory at the same time. This wastes resources. This is not ideal. You could provide a dynamically linked library. So now your package is a DLL file in Windows. You export your methods. You rely on the OS to dynamically resolve and link methods at runtime using API calls like load library or get proc address. So now you only have one DLL in memory, but you risk taking a trip to what's referred to as DLL hell, where software will overwrite the DLL that other software relies on, breaking that functionality. Also not ideal. So COM solves all of these problems for developers. The core principle of COM is to separate the library interfaces from the library implementations. Developers will define their interface to the COM standard and allow their classes to be instantiated from other processes and other languages at any point in time. Because applications and libraries need to be updated, and without changing the underlying structure of the shared procedures. So when a binary is made COM aware, it follows this standard so a program can be updated, recompiled, and third-party applications can still instantiate that class, access the necessary functions. Implementations can be changed, but the interfaces never change. So a third-party application will always be able to use that library's resources through the never-changing interface. COM uses a client-server architecture. The reusable code must be registered as a COM server. This contains the interfaces and the implementations. A COM client is whatever code wants to make use of that object and that the functions implemented by the server. This is done by getting a pointer to the COM server's interfaces and then calling the methods available. Servers can either be hosted in process through a DLL file that's loaded into another process, or an out-of-process server. Out-of-process servers are required if you want to call a COM object that's available on another machine. COM server components must be assigned physical names and logical names. So a logical name like alerts.messagebox, that might be used by two different programs. So each COM object is given a physical name that is globally unique, or a GUID. There's a lot of GUIDs in COM, but the most important GUID is the class ID. This is the identifier of the library's actual implementation. COM interfaces also have IDs, but all COM interfaces look the same. Their uniform structure allows for clients who don't know anything about the interface or the implementations to query the interface for a list of pointers which point to the actual interfaces supported for the COM library. There's only 3 methods exposed by this interface. There's a query interface that retrieves the pointers to the supported interfaces of the object, and then there's the ability to increment or decrement a reference counter of who is using the object. And COM clients really can be written in any language. COM clients, or languages that are not natively supported by Windows, have libraries to help with the creation and management of objects. But at the Windows API level, developers will often use the co-create instance API as a generic function to create a single instance of an object. This function will call the exported DLL getClassObject function, which is exported by all COM libraries. This calls the object interface's query interface method. This method retrieves the pointers to the interfaces implemented in the object, and then from there you can interact with the COM objects using a pointer to its interface. And if you don't know the class ID, the OS is capable of resolving the prog ID to a class ID using the class ID from prog ID API call. COM objects must be registered by the OS. This is done using the regserv32 binary. This will register the DLL with the OS by calling the DLL's exported DLL register server or DLL unregister server functions. And if you take a look at what this process is doing to register the COM component, it's creating some registry keys containing the class ID. Take a look in the registry. COM libraries are all registered under the software class's class ID key. Under each class ID, there will be various subkeys which define object behavior. This particular object on the screen is an in-process server because of the inproc-server32 key, which points to a DLL file on disk. So inproc-server32 or inproc-server subkeys, these are for in-process servers. The local server subkey is for out-of-process servers. The 32 suffix just indicates that the key is for 32 or 64-bit applications. A key with no suffix is for 16-bit compatibility. So this is the most important key in the COM registry structure because this points to where a COM library is located on disk. COM objects can be registered on a per-user basis. These are registered in the HKey current user registry hive. COM objects that are registered system-wide are registered in the HKey local machine hive, in both cases writing under the software class's class ID key. If you're not familiar with the HKCR hive or the HKey class's root hive, this is a virtual hive. It doesn't actually exist in the same way that HKCU and HKLM hives do. HKCR is a merged view of the class IDs from both HKCU and HKLM registry hives. If a program wants to write to HKCR, this requires privileges because writes to HKCR are mapped to the local machine registry hive. So let's do a survey of what COM objects are registered on a system. My test box for all of this was just a Windows 10 Pro box. I installed Chrome, I installed Office 2016. I wanted this test box to resemble systems that are often seen in enterprise environments. As seen in these statistics, the majority of COM servers are in-process servers, and the majority of COM objects are registered system-wide. And you can try this at home if you want. So I've wrote a PowerShell script for basic interactions with COM and COM hijacks. It'll be uploaded to this repository within the next week. I just need to clean up my code a little bit and write some documentation. If you want to see any of these objects in more detail, I recommend using the OLEview.net project. This is an open source tool written by James Forshaw for exploring COM objects on a system. Highly recommend. So if you weren't paying attention before to all the boring stuff about COM internals, I'm going to talk about the fun part now. So recall that objects can be registered either per user or system-wide. So per user, objects have precedence. Any object that's registered in the HKCU hive will be loaded before an object that's registered in the HKLM hive. The exception to this rule is high-integrity processes. They read directly from the HKLM hive because it would be trivial to escalate your privileges if high-integrity processes were reading from the HKCU hive. But if you recall from the previous survey, Remember that the COM objects were mostly registered system-wide, and although we do need administrator-level privileges to write to HKLM, we don't need any of those privileges to write to HKCU. So any class ID key that you write in the HKCU registry hive, and that class ID can point to any COM server that you want, that will be loaded before the legitimate object is loaded. Even if the key is duplicated, so when it has values in HKCU and HKLM, if the client is reading objects from the HKCR hive, it's only going to read that object that is present in HKCU. This technique is kind of the cousin to DLL hijacking. So instead of exploiting insecurities in the Windows loader process and how it finds DLLs, we're just exploiting the COM resolution process and how COM clients are attempting to locate the library for a COM server. So to uncover hijackable keys, you should use sysinternals procmon. To test this, it's the same Windows 10 Pro machine. I've got Chrome, I've got Office 2016 installed. My testing strategy was really simple. For 5 minutes, I launched each application, I let them run, I opened files, I saved files, normal user behavior. I want to find keys that are reliably triggered through normal use, otherwise it's going to be of limited value to me as an attacker. The filter I used to identify these events, so we're looking for registry keys where the result was not found. We'll further hone the filter by looking for in-proc server 32 keys, because that's going to be the majority of COM servers on a machine. I'm also going to ignore reads to the HKLM hive because that requires administrator privileges to write to. The result: in about 5 minutes, there was over 11,000 attempted registry reads to userland writable locations in the registry. That means that there's 11,000 events where an attacker's library could have potentially been loaded into another process. Take the results of this, export it to a CSV for analysis. So from the previous sample capture, you can use this command that I wrote to just parse the CSV, and from the sample that I took, there was about 628 unique class IDs that were activated across various user processes that were all launched over the 5 minutes of testing that I did. So let's write a proof of concept library and hijack one of the keys we found in the previous slides. So remember that in-process COM servers, they need to be registered they need to be implemented in a DLL file. But the good news about this is that DLL does not need to implement any COM functions I discussed previously. You don't need to implement any of the registration functions. You don't need to implement any of the interface querying functions. None of that is required. So DLL files have a DLL main function. This is called whenever a process attempts to map or unmap a DLL into its process space. It's also called whenever a process creates or stops a thread. But COM object activation is going to be loading libraries, so this seems like the best place to run some type of payload. DLL main is kind of an interesting function. It's not actually exported from a DLL, so there's a PE header which contains the entry point for the PE file. And in the case of DLLs, this is just the DLL main function. But the potential issue with this technique is that the OS holds a loader lock whenever it's loading DLLs. That lock is held before DLL main is called. The loader lock is held to ensure that multi-threaded programs don't deadlock if multiple threads within a process are attempting to change the list of modules which have already been loading this, because doing this can introduce some dependency loops inside of Windows' extremely fragile loading process. So because of this, it's not really advised to do much inside of DLL main. We're kind of limited here, because anything that could cause a lock or a hold for an extended period of time will cause the program to crash. We can't lock anything, we can't wait for any locks, we can't wait for a process to do something, we can't wait for a thread to execute, because all of these actions will cause a deadlock. Here's an implementation of DLL main. It's nothing special. This is actually just generated by Visual Studio whenever you create a library project. But what this reads is that if the DLL is being loaded into another process, signified by the DLL process attach event, let's do evil stuff. What evil stuff? Here's a basic and naive approach. Let's just spawn a new process. Alright, let's see our proof of concept. So in this POC, I'm going to show first that I have no administrator rights. I'm just a low-level user. There's no tricks up my sleeve here. So this is a GUID for a COM object. You'll see right here, and then there's the DLL that has been dropped to disk. All I'm doing here is just creating a new registry key with a GUID that exists in HKLM. So I've added the registry key. Once it's done, let's just do something that a user is going to do. Let's click an icon on the desktop. So look at the top there. You'll see that in Procmon, Explorer has loaded our DLL, and we have a calculator. So spawning calc is a cool proof of concept, but I'm a red teamer. I can't always be spawning processes. AV and EDR products, they're very good at catching process creations, and I probably don't want to do this in an actual environment I'm testing. So remember, in LoaderLock, we can't load any libraries. We're going to be limited. Sorry, VMs are freaking out here. We can't load any libraries in LoaderLock. We're going to be limited to what's already loaded into the process's memory space. But we know that kernel32.dll, that's always going to be loaded. And this gives us quite a few functions we can use, say, to get a handle on a process, maybe allocate a chunk of memory, write some shellcode to that memory block, and then create a new thread. You know, everything that we need to do for shellcode injection into another process. So in this demo, I'm going to show that from DLL main, we can call Windows API functions just required to inject shellcode into another process and then have it run. So in this demo, I'm hijacking a class ID that I know is called by Chrome.exe. We're adding the registry key again. So just watch Procmon at the top. You'll see that as we launch Chrome, Chrome has loaded our DLL. This time it's Notepad, but if you look on the right, you'll see in Process Explorer that Notepad actually spawned from Explorer. This is just showing that our shellcode, even though it was launched from Chrome, it was run inside of the Explorer memory space. So now we're not spawning any new processes, but there are still some downsides to this technique. Most importantly, injecting shellcode into other processes, this is a very well-known technique to AV and EDR. Hell, to even run that proof of concept, I had to disable Windows Defender. But there are a lot of other techniques for process injection that I didn't really test. That's kind of out of scope of this talk. There's a collection of different injection techniques on the EvilBits GitHub repository. Create Remote Thread is definitely the most well-known and well-signatured technique. So just by changing this technique to a more obscure process injection technique could make this technique usable in the field. So some of you are probably asking, well, why don't I just create a thread inside DLL main? And that really would be the best case. If our DLL can continue to live inside of the COM client's process without creating any new processes, without calling any suspicious APIs to inject shellcode into another process. But whatever threads we create inside of DLL main, the thread entry point is not going to be called until the LoaderLock is released. But there is another function that we could possibly use here. So the DLL get class object function, this is exported by all COM enabled DLLs. This fetches the class objects implemented in the library. This function is called whenever a COM object is activated, and there's no loader lock that's held when this function is called. So we can try to keep our DLL loaded in memory by not returning the OK sign whenever DLL can unload is called. So this is called pretty regularly when a process is trying to free up modules that aren't needed anymore. But we do have some other problems outside of this. So when you're hijacking a COM object, you're preventing the process from loading a library that it needs to function properly. So the process goes to the registry to find its COM server. It gets a library it is not expecting. The library doesn't have the right exports. The name and the path aren't what's expected. We aren't implementing any of the COM interfaces. It's just not acting right, so there's going to be potentially catastrophic side effects. Other than just complete program crashes, you could get random error messages. Certain UI elements might glitch or misbehave or just not respond at all. And without reverse engineering the COM client, we can't know for sure what that behavior of a hijack is going to be. So while some class IDs do cause crashes and misbehavior when hijacked, There are a lot of class IDs which really don't care what the hell happens. They'll load any DLL, they don't really care. A few examples of such keys. How did I find them? So I created another proof of concept library. So we're creating a thread in DLL main, and we're creating another thread in DLL get class object. In my proof of concept, these threads are just updating a file with an incrementing number, but obviously you can change this to do whatever activity you desire, as long as you remember the caveats of running a function when the loader lock is held, and that threads created in DLL main won't start until DLL main exits. So let's see what this looks like. So in this demo here, I've got 6 different class IDs I'm going to hijack all at the same time, just using the hijack multiple keys commandlet that I wrote in my PowerShell COM hijack toolkit script. But what this commandlet is doing on the back end, we're just going to load a unique DLL for each class ID hijacked. You'll see this just because it's each class ID we're going to hijack, it's a DLL with just the name of the class ID, just so we can keep track of who is loading what. But once the keys are hijacked, we're going to launch Explorer, and this time there's no calc, there's no notepad. Instead, when the DLLs are loaded, we're just starting some threads that are logging to a file that's unique per class ID and per thread created. So just by observing the size of the log files, we know that the thread is still alive and running our code. It's important to note here, though, that DLL get class object, this can be called potentially several times within the same thread. So in which case, you might get a file, not like this, but you could get a file where there's multiple threads writing to the same file. So you do kind of need to make sure that the code you write is thread safe, but that's out of the scope of this talk, and I really wish you the best of luck writing thread safe code, because it really sucks. There may be some cases where dropping a DLL into the target environment might not fly. So this technique was originally documented by Casey Smith and Matt Nelson in their 2017 talk, Windows Operating System Archaeology. So instead of registering a malicious DLL, a COM hijack can register scrobj.dll. So this is a legitimate Microsoft binary. This is already on the system. And then by using the scriptlet URL key, you can associate a Windows scriptlet file to run when the object is activated. And this can be a file that's on disk, or this can also be a URL to a scriptlet file. And this is really cool because if you choose to host that scriptlet remotely, this is almost fileless. Like, you're not dropping anything to file, you're only adding a few registry subkeys. This is not a common occurrence, though. I haven't seen any legitimate uses of the scriptlet URL key on any systems where I've looked at those, so Blue Team, take note. Let's see a demo of this. So I've got this scriptlet file. That's the GUID that we're going to hijack. The payload is just creating our favorite wscript.shell COM object and using that object to start calc.exe. So we're going to hijack the DLL, just a local path of the scriptlet file, but this could be a URL to a remote file. So we click on Explorer. There's our calculator. So you see that Procmon is on this screen as well, but scrobj could already be loaded into Explorer, in which case you won't see that load image event. But on the top right, let's look at the registry structure required for this style of hijack. So this is the improc server 32 key, just pointing to scrobj DLL that already exists on the system. That's a Microsoft DLL. And then the scriptlet URL key just pointing to the location of our scriptlet. Another slightly different variation on this hijack technique is to take advantage of class IDs in the registry that point to a DLL that doesn't actually exist on disk. This gives attackers the opportunity to write their DLL to that location and potentially have it loaded without any type of registry modifications. This only requires dropping an executable file to disk. Now, in most cases, especially with Windows processes, these libraries are going to be stored in C Windows System 32. That's going to require administrator privileges to write to. But a lot of third-party software, especially software where components are removed or maybe the software has been uninstalled, may leave behind keys in the registry. So here's an example key that was left behind by an older version of Chrome, and I guess Disclaimer, this folder does require administrator rights to access to, and there's also no promise that that class ID is ever going to be activated, especially if it's a component that's been removed from the software, but it might be activated, and there's other ways where we can use this that I will demonstrate later. Another alternative method is by hijacking the prog ID. So remember, the prog ID is the friendly name of an object. It's not guaranteed to be unique, but COM clients can ask the OS to resolve a prog ID to a class ID. And this is done in the registry. So prog IDs are mapped to class IDs in the software classes registry key. So if you just add a registry key into HKCU software classes, you add a prog ID that points to a class ID that you've added that is loading your library, it'll be hijacked, and the attacker just needs to create the key, have it point to the DLL or executable of their choosing. Another alternative is the abuse of COM's treat as emulation feature. So treat as key means that a class can be emulated by another class. So all activation requests sent to the original class get forwarded to the class ID specified in the treat as register key. This just means that if we want to do a hijack, we need to create a new class ID with a GUID pointing to whatever COM server that we want, and then we add a treat as key to the class ID that we want to hijack. You point that to the class ID you created, and then whenever that object is activated, you've hijacked the object. So where can we use COM hijacks in our attack chain? As demonstrated, COM hijacks are exploited by dropping a DLL to disk, maybe making some registry key additions in the HKCU hive. We have several different options available for which keys we add and what kind of files we want to drop to disk. We chose class IDs, which were often activated because as an attacker, I have an interest in having my code persistently run on a machine across reboots. The attacker's code is going to be called whenever that object is activated. So whatever type of key you hijack, whether it's on process start or maybe it's some regularly run task, you'll have your code run. This technique doesn't necessarily require any reboots or process restarts unless, of course, the object you're hijacking is only triggered on startup. This technique is also interesting because COM hijacks are not detected by the sysinternal's autoruns tool, which is a very popular forensics tool. So just last week, my friend Leah released a really cool piece of code. So if you look at the signature of DLL get class object, this contains an argument for the object's class ID. So with this information, we can go out to the registry, we can find the location of the legitimate COM library, we can load that library and then call the library's exported DLL get class object function and effectively proxy the COM objects through to the legitimate library. This means that we won't cause any system instability as demonstrated previously when we're hijacking an object. A variant of this technique used for persistence, this was previously documented by Matt Nelson of SpectreOps, but if you look through the scheduled tasks on a system, you may see tasks with the custom handler action. What is this? It's a COM object. So scheduled tasks with a COM trigger, they're ripe for hijacking. All you have to do is hijack that object, make sure that scheduled task is scheduled to run, and you can run that without the risk of corrupting the runtime of another process. Here at a PowerShell script that you can use to identify these scheduled tasks on a system. Another technique we might be able to use this for is process injection. So to evade like AV or EDR detections, an attacker usually wants to do some type of process injection to have their malicious code running in another process's address space. This is a very well-known evasion technique. Just by using another process's cover, an attacker might be able to interact with files, send traffic over the network, all from the process space of well-known trusted executables like explorer.exe or chrome.exe. And because chrome.exe, it has to send network traffic, maybe it's just going to get a pass from EDR for sending traffic to whatever C2 server you're using. The actual techniques for performing process injections is really a game of cat and mouse. So I demonstrated in my second demo, we created a thread in DLL main. We injected some shell code into the Explorer process using the create remote thread API. that's really just one technique. There's a lot of other techniques. There's APC injection. You can do process hollowing. You can do thread hijacking. There's a lot of documented techniques for performing process injections, but COM hijacking is not really considered a vector for performing process migrations, and I don't understand why not, because well-tuned security products, if it's using like machine learning or AI or blockchain, they're going to know about these API calls. So any program that we create that's calling these functions to perform process migrations has a solid chance of being flagged as suspicious. So through registry modifications only, I've demonstrated that we have the ability to have our code loaded into other processes. So just by knowing which processes call which class IDs, we can hijack a COM object, have our object injected into a more favorable process, and avoid using these suspicious API calls altogether. The only drawback of using this technique is that there could be some kind of time delay. Until the COM object is loaded and triggered, we're not going to be able to inject where, using create remote thread, that injection is going to be performed almost instantaneously. I really wanted to show a demo of this technique, but the demo gods are not kind. I couldn't get it working last night, so I'm going to have a proof of concept of this within the next week. Sophisticated adversaries, they have an interest in making their activities appear benign. So using COM hijacking in conjunction with other techniques, an attacker has a couple of different options for misdirection. So none of these techniques that I'm about to talk about, they don't require a COM hijack, but when combined with the COM hijack, it can augment an attack chain that could bypass whatever detective controls are present in the environment you're operating in. So first of all, application whitelisting bypasses. There's several documented Microsoft programs which take a class ID or a prog ID as an argument. RunDLL32 is the most well-known, but there's others. There's XWizard, there's the Verified Class ID executable, MMC. These all take COM objects as arguments. So a great place to use this as an example would be after hijacking an abandoned key. So I mentioned it might not, an abandoned key might not regularly be called by a process. So by using these binaries, you could drop a DLL to disk, call a Microsoft signed binary on a class ID that already was already on the system, and then have your code loaded into another process. Another activity this could be used for is lateral movement. So this technique was originally documented by FOHOPS, but if an attacker has administrative access on another host, they can use the remote registry to perform the hijack. They can drop their COM server to disk, and then they can either use DCOM to activate the object remotely, or they could just wait for the object to be activated through normal user interaction. So what are all the takeaways for red teamers in the room? So I think COM should be incorporated into multiple stages in your attack paths, and because this is not a very popular technique, I think it has a place in everyone's offensive toolkit. I've shown that COM hijacking is a cool way for userland persistence. This technique is not really widely used when compared to techniques such as registry run keys, scheduled tasks, WMI subscriptions, so it can put you at an advantage. COM interface abuse also gives attackers a layer of misdirection by appearing to use components of other processes. This technique could confuse EDR signatures, or maybe even like a tier 1 analyst, so they're of value. Initial access is another area where COM hijacks can be abused. So since COM hijacks are really just causing applications to run our code, why don't we see any stage 0 loaders that are just dropping a DLL to disk and then hijacking that object and having the code run? Hijacks also have the potential to be used for migrating into other processes to evade detection or to get access to that process's memory space without using suspicious API calls like create remote thread, which is well known to defenders. Certain processes like Edge or Internet Explorer on newer versions of Windows systems, these use Microsoft Code Integrity Guard. This is preventing unsigned DLLs from being loaded into the process at a kernel level. But these are not, the only processes where developers don't want you loading additional libraries in their processes. Hardened applications such as browsers or maybe like anti-cheat engines, they're actively preventing DLL injections. They don't want unsigned or untrusted code loaded, and they're going to accomplish this through hooking of different API calls like create remote thread or load library to prevent these functions from being used to launch code that isn't explicitly whitelisted by the developer. But with COM hijacking, it could still be possible to bypass these mitigations and load a DLL into a hardened process without any of the traditional techniques. What are the takeaways for the blue team in the room? So what I just said to the red team, do you know if people are abusing COM in your environment? Like if you're not watching for registry key additions under HKCU software classes, class IDs, you should be. These registry keys should be treated with much suspicion and should be as closely watched as you watch run keys or scheduled task additions. HKCU class IDs aren't common as seen in the survey I conducted, so the false positives here should be pretty low. Inproc server 32 key additions are already monitored by Swift on Security sysmon config. You should also pay special attention to scriptlet URL or treat as keys because these keys can also be used to load malicious objects. If an attacker already has administrative access on a machine, they do have the option of using any of the techniques I've talked about, but on the HKLM Hive. They can overwrite a key location with a DLL, they can hijack prog ID resolution, they can try to emulate a class with treat as, but HKLM is owned by Trusted Installer, so an attacker who does want to go this route of COM abuse as an administrator, they'll be required to change registry key permissions before conducting a hijack. Blue team members should also be checking systems and golden images for abandoned keys. So exploiting these abandoned keys doesn't require any kind of registry modification. So if you're only watching for registry writes in HKCU, you could miss an attacker exploiting an abandoned class ID. If you're developing security-sensitive applications, or maybe if you're reviewing an application that runs in user space, don't rely on the OS or the registry to locate COM objects. Don't use co-create instance. Instead, you should try to identify the location of the library on disk manually. Check the registry, check the file system, make sure that this is a library that you're expecting to load. Then you can call load library and directly call the DLL get class object on the DLL, still use all of the COM features without relying on the insecure registry lookup procedure. And this only applies to userland processes because elevated processes, they're going to read directly from HKLM, which makes this type of abuse impossible. And if you're removing an application component or if your application is being uninstalled, please clean up the registry. Don't leave dangling references to DLLs that don't exist on the system that an attacker would be able to abuse. I think there's a lot more that's possible through COM abuse that I didn't have time to talk about today. So I didn't really talk about hijacking out-of-process COM servers. There could be other registry keys that are abusable in the same way that prog ID or treat as is. Frida is another really cool project. So this is used for reverse engineering and debugging. I think it can be used to get a better understanding of COM client behavior when it's activating a COM object. What kind of specific user actions will trigger loading a particular class ID. COM hijacking also gives the attacker the ability to hook calls between applications, read or modify their contents, access sensitive data, change application behavior. This could be very interesting to an attacker. There's also been some documented hijacks that give bonus effects when hijacked. A few examples of this. So Matt Nelson was able to disable the Microsoft anti-malware scanning interface. This just gives AV programs visibility into script executions, but he was able to do this. He was able to prevent the AMSI DLL from being loaded through a COM hijack, and that's really cool. James Forshaw was also able to demonstrate a COM hijack, which was part of a larger attack chain, but he was able to execute code inside of Ring 0, inside of a VirtualBox kernel driver, which a COM hijack assisted with. So I'm sure there's other keys out there that when hijacked could maybe prevent some type of EDR solution from accessing a DLL it needs. There's a lot of stuff here that I didn't really have time to look at. So what am I going to be releasing on GitHub? So I have a PowerShell script that's used for basic surveys of systems, parsing data related to COM hijacking and performing hijacks. I'll also be releasing all the proof of concept DLLs that I wrote for this presentation. There's 2 proof of concepts that run a payload inside DLL main. I'll release the DLL which measures thread lifetimes after the library has been loaded. I'll release a proof of concept for performing process migrations only using COM hijacks. I expect to have this up within the next week. I just need a little bit more time to clean up and document my code. I really stand on the shoulders of giants here. My presentation would not have been possible without the help of some of my friends, without the support of NCC Group research directors and other researchers who have published their findings on COM abuse. So thank you to all of these people on this slide. Does anyone have any questions? Over there. So that is definitely possible. The reason I didn't really go that route is because you would have to do that for every DLL that you want to hijack, and that would be a lot of work. So I think the kind of proxying technique that I showed in Leo Lubeck's COM proxy project is kind of the most effective and efficient way of doing that. Any other questions? Yeah. Can you speak up? I can't hear you. Can you speak up? I can't hear you. So, I mean, the PowerShell script is more for just kind of research. I'm really not expecting you to be loading this PowerShell script, inside of some environment, because I mean, PowerShell is pretty suspicious these days. So the PowerShell script is more for just on your own test system, identifying these hijack events, and then using that on a different system, which you might have a little less control over. Does that answer your question? I mean, there's no way to block this or prevent this from happening, and I other than the sysmon config that monitors the improc server 32 key additions, I don't know if anyone's really scrutinizing that subkey to watch for these hijack events. So I think Endgame had a blog post about COM hijacks where they were like, "Oh yeah, we'll detect this," but I mean, I haven't been able to test it on an Endgame, Endgame product. Other than that, I don't know of any other products that are explicitly detecting this kind of activity. Yes. That completely depends on the environment you're operating in. I can't answer that question. I mean, not being able to drop a DLL to disk using the scriptlet URL hijack, I mean, that could work, but like I said, scriptlet URL is not a common occurrence, and I think newer versions of Windows have the Windows Defender, it's WDIC. I can't remember what it stands for, but it prevents the ScrobJ DLL from loading untrusted scriptlet files. It depends. I can't really answer that question. Anything else? All right, if there are any other questions, I'll stick around outside if you want to talk about COM or talk about other techniques that NCC Group is using on our red teams. I'd love to talk to you, but thank you everyone for listening.